Hey everybody, welcome to Graphing Radical Functions Part 2, and by that I mean graphing cube roots now. So we took a look at graphing square roots, now it's time to take a look at a different type of root, and that's a cube root. Notice the change in how the graph looks. That's the big feature here. That's the only thing that really changes is the general shape of the graph. How we do it stays the same. So let's take a look at that parent function then. So for this one, we're going to be talking about cube roots. You can see that right there. That's the type of root we have. So when we choose x values to plug in right here inside the cube root, we'd want to do x values or numbers that we know we can take the cube root of. Without going too large, I know we're pretty familiar with the number 8 as a perfect cube to this point, so it might be wise to do numbers like -8. We can cube root a 1, so -1, 0, 1, and +8. All of these numbers are nice cube rootable or perfect cube numbers that we can actually figure out. So what is the cube root of -8 when we plug it in right there? What times itself 3 times makes -8? 2, right? What about -1? What times itself 3 times makes -1? -1. 0, cube root of 0 is 0. Cube root of 1 would be 1, and cube root of 8 would be 2. So now if I make a little picture of what this guy looks like, -8, -2 would be over here, -1 right here, 0, 0, 1, 1, 8, 2 right there. This is what a cube root graph looks like. So it doesn't have the starting stopping motion, if you will, of the square root. It's continuous. It has arrows on both ends because you can cube root negative values. So we have this sort of wave-ish looking thing here, or I don't know what you would call it, a ribbon, if you will. But this guy right here is what a cube root graph looks like. Now the domain and range then, we would go from -infinity to +infinity for x values because of those arrows on both ends, and the same for the y values because of those arrows on both ends. So domain and range, or you can say in the shortcut way, I guess, without the notation of infinities, you could say the domain includes all real numbers, which is the R with the little extra line down there, and the same thing with the range, all the real numbers in the world. So we have a parent function graph here, and this is what all of the cube root graphs should look like. So let's take a look again at how those transformation works. It's the same thing, now just a cube root. So still in front, our vertical stretch or shrink, making it taller or shorter. Inside, moving it left or right. Outside, moving it up or down. Let's take a look at how that works on 3 examples here in this a little bit shorter video, okay? So again, let's start with that parent. The parent table was -8, 2, -1, -8, -2, 0, 0, 1, 1, and 8, 2. You don't have to do all of these points, ladies and gentlemen, but this is what that parent function looks like. Now in front, we're talking about the number 2 in there. That means he's going to be stretched 2 times taller. So stretch times 2. So we're going to keep the same x values of our little table, but we're going to make the y values 2 times taller. So instead of being at -2, now it's at -4. Instead of being at -1, now it's -2. 0 multiplied by 2 is still 0. 1 gets multiplied by 2, making 2, and 2 gets multiplied by 2, making 4. So this is my stretched graph. I am now at -8, -4, so down here, -1, -2, right here, 0, 0, 1, 2, and 8, 4, right there. So notice how it's quite a bit more wavy here because of that 2 stretch factor. Okay, that was my stretch graph. That's not the final answer, but it gives me points that I can now move according to these shortcuts. So remember, inside's a +4. I'm going to go left 4 and down 3 with each of those dots. So left 4, down 3 with the 0, 0 dot. Left 4, 1, 2, 3, 4, down 3, 1, 2, 3, this dot. This dot right here going left 4. Ooh, I can't fit him on the graph, right? If I go left 4 from this one, so I'll stop doing that one. This one right here, left 4, 1, 2, 3, 4, down 3, 1, 2, 3. There he is. And this last dot up here, left 4, over here, down 3, 1, 2, 3 here, and I'll connect my shifted dots here. This is my final answer. Now again, because those arrows are on both sides, if you want to, oh, I should say before we go to domain and range, if you want to, you can erase this stretched one here because that was just the points that allowed me to get there. You don't have to go ahead and draw that one if you don't want to, okay? It was just the points that I needed that would help me move left and down. You can also do it with the table. You know that moving left affects the x values, makes them 3, or I would subtract 4 to move left. And then I would also go down 3, so I'd subtract 3 from my y values, and you can make a new table if you'd rather do it like that. But in the end, we need to make sure we get in that final region, just like we did with square root. Because there are arrows on both ends, the domain and range are easy. All real numbers, all real numbers. Nothing to worry about there. We don't have a starting spot to even think about. There's arrows on both ends, so negative infinity to positive infinity. Okay, let's do a second example. The parent again, -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. And we're going to do what this guy says first. So that says I need to do a flip. So -8 now goes to +2, -1 to +1, 0, 0, 1 to -1, and 8 to -2. So if you want to draw that flip, you can, but remember that's not my final answer. I'm going to do this one using the table idea. If you would rather change the table rather than counting the dots here, that's fine. So this motion in here tells me I need to go to the left 2. This one out here tells me I can go up 4. So I can draw these on the graph, put on graph if you want to, or you can change the table, or I guess we would say edit the table values using our description. I'll show you how to do it on this one. Okay, so if I was going to go to the left 2, let's say I'm starting at -8 here, and if I'm going to go to the left 2, where would I end up? Right over here at -10. So that means I can just subtract 2 from each of those table values. So now -8's gone to -10, -1's gone to -3, 0's gone to -2, and 8 or 1 has gone to left 2, -1, and then 8 has gone left 2, subtract 2, so 6. So now I've done the left 2 to that column. Now I can do the up 4 here. So up 4 more makes 6, up 4 more makes 5, up 4 more makes 4, up 4 here makes 3, up 4 here makes 2. So this would be my final answers table if you'd rather graph it that way. So -10, 6, -3, 5, right here, -2, 4, right here, -1, 3, right here, and 6, 2, right here. Some people like graphing it with the table. Others like to just graph the stretched one and count the boxes. It doesn't matter to me. Okay, but you know the domain and range will always be all real numbers here, so you don't have to worry about that at all. Okay, let's do third and last. So example 3, again, the parent function starts us off. We need that table, -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. And then from there, we can edit. So this guy right here, a 1/2 in front, so that's a shrink. Shrink times 1/2. So I'm going to take my table values. -8 stays the same. Shrink does not affect horizontal motion. It affects how tall the graph is. So each one of these gets multiplied by 1/2. Here, these y values, and I get -1, I get -1/2, I get 0, I get 1/2, and I get 2 times 1/2 is 1. So I have these new table values. Again, you don't have to graph this one if you want to. You can edit the table by moving left, up, down with just the numbers. But I will graph this one more time so you can see how this works. -8, -1, -1, -1/2, 0, 0, 1, 1/2, and 8, 1. So there's my really small ribbon looking thing here, not really gradual, not a straight line, but kind of gradual. And then from there, each of those dots can move this motion of left 3, down 2. So I can take each of these dots to the left 3, down 2, that's that new dot, to the left 3, 1, 2, 3, down 2, right here, to the left 3 here, down 2, 1, 2 here, and to the left 3, down 2 would be here, and then this one to the left 3, down 2 here, and I can draw in my final ribbon looking thing here. Whoosh. There he is. This one is my final answer. And again, you can erase the other one if you want to. Domain and range, all real numbers, ladies and gentlemen. Same idea as what we did with square roots, just different looking starting parent. So it changes the way the graph looks, but the rules still operate the same. Thank you for taking good notes. Kincaid out again.